Welcome to this explainer. Today, we're going to completely demystify how a spacecraft can actually navigate and orient itself in the vacuum of orbit using entirely natural forces. Yep, we are talking about pulling off some incredible engineering feats without using a single drop of electrical power. It's a completely fascinating concept that basically turns the Earth itself into an invisible space compass for our satellites. So let's dive right into the seemingly impossible challenge. I mean, when most of us picture a spacecraft, we're imagining roaring thrusters, intricate reaction wheels, glowing sensors, and these massive solar panels feeding complex onboard computers, right? But what if you stripped literally all of that away? How exactly do you steer a chunk of metal flying at thousands of miles an hour through orbit with absolutely no motors, no electronic sensors, and zero electrical power? Well, the big secret here is that we're relying entirely on the Earth acting as a giant magnet to orient the craft. This brilliant little technique is called passive magnetic stabilization. Instead of fighting the environment with fuel and electronics, this method just works with it. Because the Earth produces this massive magnetic field around the planet, we can actually use that field to naturally control a spacecraft's attitude. And by the way, attitude is just the fancy aerospace term for its orientation. Think of it like this. A permanent magnet placed on a spacecraft experiences a physical torque that forces its magnetic dipole to align directly with Earth's magnetic field. It is exactly like holding a compass in your hand while you're out on a hiking trail. You know how the compass needle rotates until it points north because of the magnetic torque acting on it? Well, a satellite with a permanent magnet behaves in the exact same way up in orbit. It's just elegantly simple physics. But that brings us to part one. We need to talk about the missing piece here, which is damping the endless swing. Because yes, a permanent magnet absolutely will pull the spacecraft into alignment, but we have to remember the environment we're dealing with. Space is essentially frictionless. If a spacecraft only had a permanent magnet, it wouldn't just magically stop on a dime the second it reached the correct orientation. Oh no. Instead, its angular momentum would cause it to overshoot the target, swing back, and violently oscillate for a really long time. It would be way less like a precise instrument and more like a chaotic theme park ride. And obviously, that would be entirely useful for any kind of stable mission. So to make this actually work, we really need two contrasting components to team up. The permanent magnet acts as the muscle, pulling the craft into alignment, while these clever little things called hysteresis rods act as the essential shock absorbers. These hysteresis rods are made of soft magnetic materials, and here's the cool part. As the spacecraft swings back and forth, these rods repeatedly magnetize and demagnetize. In doing so, they literally absorb the rotational energy of the spinning spacecraft and convert it into tiny amounts of heat. They just bleed off all that excess energy until the craft completely stops swinging. Moving on to part two, let's look at the orbital choreography. How do these pieces actually work together in practice, step by step? Picture this. The spacecraft is forcefully released from its launch vehicle, tumbling around like a lost tourist in a completely arbitrary orientation. Right away, Earth's magnetic field grabs hold of that onboard permanent magnet, creating a torque that whips the craft around. Now it flies past its target alignment due to angular momentum and starts to swing. But with every single swing, those hysteresis rods are hard at work, absorbing that energy as heat. It's just like hanging a bar magnet from a string on Earth. The permanent magnet provides the alignment force, while the hysteresis rods act as the friction that gradually slows the whole motion down until it finally settles into a stable, focused orientation. Now for part three, trade-offs and limitations. Because while frictionless space choreography sounds utterly perfect, we are, unfortunately, still bound by the pesky laws of physics. Now, the primary advantage of this system is zero. Literally zero. It requires zero electrical power to operate, it has zero moving parts that could potentially break down, and it needs zero electronic sensors to figure out where it is. Because of this power of zero, the system is incredibly lightweight, remarkably low cost, and just highly reliable. For satellite engineers, this is an absolute dream scenario. But yes, while it's brilliantly simple, the catch is pretty significant. First off, it really only works right here near Earth. If you send this spacecraft out to Mars, the Moon, or deep space, the magnetic fields are either completely absent or just way too weak to rotate the craft. Second, the accuracy is, well, kind of loose. You're looking at pointing errors of several degrees or even worse. Third, it won't point at a fixed static location like the sun or a specific star. Instead, it constantly changes orientation as it flies through its orbit, actively chasing the varying local magnetic field vector of the Earth. And finally, the response time is incredibly slow. Depending on the spacecraft's inertia, it can actually take several hours or even several days just to properly align. All right, part 4, passive versus active control. Knowing those strict limitations, how does this purely natural system actually stack up against the expensive, high-tech alternatives? So there's a pretty severe dichotomy in spacecraft design here. On the purely passive side of the spectrum, you've got the cheap, elegant simplicity of stabilization using basic permanent magnets and absolutely zero controllers. But on the active side, systems rely on magnetorquers, which are basically electromagnetic coils that you have to continuously pump electricity into just to create a magnetic field. Active systems require precise magnetometers, attitude sensors, and complex onboard algorithms just to function. You definitely get much higher pointing accuracy with the active system for sure, but you end up paying a heavy price in increased mass, cost, complexity, and a continuous drain on your electrical power. Which brings us to part 5, real-world applications. You might be wondering what kind of modern spacecraft actually utilize this passive setup today. Turns out it's actually the perfect solution for the smallest of our orbital explorers. Many early university CubeSats utilize this exact permanent magnet and hysteresis rod combo. Think about it. When you're building a tiny 1U to 3U satellite for an educational or tech demo mission, you simply don't have the space or the budget for expensive reaction wheels or super complex attitude control systems. This passive approach provides a stable enough orientation for basic communication experiments, keeping the whole mission incredibly lightweight and affordable. However, because typical pointing accuracy is several degrees or worse, you really have to choose your missions wisely. You will absolutely never see passive magnetic stabilization on anything requiring a steady, focused eye. If you're building a multi-million-dollar space telescope, trying to snap a high-res photo of the Earth's surface, or trying to hit a tiny optical communication laser target, yeah, this system is entirely unsuitable. It just cannot provide the rigid, precise pointing those advanced instruments demand. And that brings us to a really fascinating final thought. We've seen just how elegantly we can surf the magnetic field of our own planet, using nothing but basic physics and zero power. But since the magnetic fields around Mars and the Moon are simply too weak for this ingenious compass trick, we really have to ask ourselves, how are we going to elegantly navigate the deepest, darkest frontiers of space when we finally leave Earth's magnetic embrace behind? What other invisible forces are out there just waiting for us to harness them? Thanks for joining me on this explainer, and keep looking up.